For quite a while now, you've probably seen us creating Lichtenberg figures inside of solid acrylic by shooting it with high-speed electrons from a particle accelerator. It's a fascinating process, one that we've covered in detail before, and up to this point we've tried all sorts of shapes and sizes, mostly squares and rectangles, but more recently also some discs. We've never pushed beyond that into a truly three-dimensional medium, at least not beyond the natural depth that results from charge diffusion. But suppose you actually wanted a cylindrical discharge. Suppose you wanted that lightning-like dielectric breakdown to trace its way through a bottle, just like in the literal interpretation of the phrase. Well, that's exactly what we set out to do. And today, we're showing you how we managed to, quite possibly for the first time ever, capture lightning in a bottle. Now, starting out, we already knew that electrons coming out of the particle accelerator tend to deposit around a certain depth depending on their energy. We usually like to keep that around half an inch. That way, for most of our acrylic blocks, there's a nice accumulation of charge right around halfway through the material. But for a cylindrical object much larger than our usual sheet thickness, this becomes a lot more difficult. You can see pretty easily that irradiation from just one side wasn't going to cut it. Electrons would have to come in from all angles about the central axes to guarantee a uniform radial distribution of charge. And since we definitely can't rotate the particle accelerator, it becomes obvious that the object itself would have to be rotated. Now this task may sound easy, but what really complicates it is the fact that any mechanical assembly that would be used to rotate the object is going to be facing one of the most extreme environments on the surface of the planet. We're talking about enough radiation that a person would die in mere milliseconds, and most electronics would not fare much better. Not only that, objects we irradiate in the accelerator only see direct beam exposure for a very short amount of time. If a rotating cylinder passing under the beam were to spin too slowly, charge would really only be injected into a single region, and this would look pretty boring when it came time to discharge it. Altogether, this meant that we had to engineer a solution with two requirements in mind: radiation hardness and a high speed of rotation. The design that I eventually decided upon is fairly simple and operates in a very similar way to a 7-Eleven hot dog roller that you might have seen before. A brushed DC motor powers a gear train that has staggered coupling to printed rollers every other gear, and this is powered directly by a 12-volt lead-acid battery. Though heavy and bulky, I don't really have to worry about this battery in an extreme radiation field in the same way that I would have to with a more energy-dense LiPo, and only a thin lead sheet will be used to stop electrons from penetrating through the plastic enclosure. This is likely still just an unnecessary precautionary measure. Lead-acid batteries are already pretty radiation hardened as far as batteries go, and there's not much a bit of radiation can do to disrupt their electrochemistry. Aside from the battery, motor, wire, and bearings, everything else in this assembly is just FDM printed black PETG, which from our experience remains pretty reliable as a structural material even after pretty extreme doses of radiation. To make sure that a 2-inch diameter bottle would receive an even dose during even just 1 second of beam exposure, I had to make sure I selected a motor with enough speed to fully rotate the bottle at least 3 times per second. And with a little bit of math involving the diameter of the rollers, this works out to about 150 RPM. Now that we had a pretty versatile roller assembly suited for the Linac, we needed to get a hold of some acrylic bottles. We first used CAD to come up with the design that you see, and scaled it to make sure that the diameter was about 2 inches, well suited for the rollers. Then we just exported this as an STL file and sent it out to get manufactured from acrylic stock. Planning ahead for the likely possibility that one of the bottles would not respond to irradiation in exactly the way that we like, we ended up ordering 2 of them, and as you'll see later in this video, that ended up being the right move. Now once we had the bottles in hand, it was time to properly test out the hot dog roller assembly. Just to show that this is fast enough rotation, I wrapped one of the bottles in marked paper, and this gives a pretty good idea of how fast it's rotating in real time. Finally, at the accelerator facility, we placed the full assembly onto a moving cart, making sure that every component was held firmly in place with the aid of a printed mount that was placed underneath. We then set up our radiation shielded GoPro, something you should definitely check out our recent video on if you haven't already, and started recording so that if all went well, we would have some incredible footage of the bottle's mid-irradiation from inside the Linac. And all did go well. So for the first time in history, watch as true lightning in a bottle forms before your very eyes.
closely. When every line is considered, every detail refined.
No, we don't. No, just send it.
Lower,
Send
lower.
it.
Roll it. Okay. Put it. We're good?
Yes. Go.
Hand in.
Oh, yeah. Okay. Oh, yeah.
Now the result of discharging this bottle intentionally looks incredible. But what may be even cooler is to see what happens when the bottles are unable to handle the charging process and undergo what we call self-discharge under the beam. Let's take a closer look at those final products with the Sony 90mm macro. What I think is really cool about these cylindrical designs is that the surface curvature refracts light at different angles, making it seem as if the Lichtenberg figure inside is larger than it actually is. Looking head on through the center, you can see that it's actually not that huge, instead forming a hollow tube-like structure with pretty even spacing from the outer surface. You can also see the clear differences in internal structure between the bottle that we were able to manually discharge and the one that popped second while still in the Lenac. I also designed and printed an LED lighting base specifically for highlighting the incredible features of these bottles from below. So if you think this makes for a pretty cool desk ornament, we've decided to auction one of these off on our eBay. That listing will become active at the moment this video comes out, so just check out the video description if you're interested. The roller assembly shown in this video is sure to make another appearance in the future, so give us your ideas of things to irradiate using it, and we'll be sure to try them out. Thank you guys so much for watching, and we hope to see you guys in the next video.
These are Anaglyph 3D glasses, and they're super cool. One lens makes you see the world in red, the other in blue. In computer terms, it would be like splitting an image into the RGB channels and selecting only the red or blue one. So that got me thinking, what if you write a hidden message in the red channel and cover it up with gibberish on the other ones? Let's see. That looks quite well hidden. You can only read it clearly when you look through the red lens. I think it's already obvious where I'm going with this, so here's an outline of what I wanna make. You're kinda lost in this lab or whatever, damn, that's super original. The place doesn't matter for now, but it has those monsters in it. Now you can only see the map and UI when you look through the blue lens, and the monsters with the, you guessed it, red lens. It's hard to even picture what kind of effect that's going to give. Imagine seeing two different parts of the same game with each eye, so make sure to keep watching to see how it turns out. Anyway, let's get to work. Say hi to this creepy guy, let's call it Eye Floater. I covered it up with random green, blue noise and other stuff. Here's how it looks like, can you find them? When you look through the red lens, you can see them clearly, and with the blue lens you can see them even less than before. By the way, if this video looks like it's in terrible quality, that's not because I can't animate an even remotely normal looking work cycle. It's because YouTube really hates random noise in videos, which this game is gonna have a lot of. Basically, videos like this are really hard to compress, so they lower the quality to save server space. For that reason, and also to save you guys from epilepsy, I'll be keeping these visual effects off whenever I can. Okay, let's get back. We need a way to kill our foes, so I made a simple shooting mechanic. It's nothing special, just press to attack what's in front of you. If you miss a shot, you can pick the bullet back up. Also, the shooting effect is wide, so it's clearly visible no matter which lens you're looking through. Now our main character, his name is Red with 2 R's by the way, say hi to him, can kill all enemies and escape the lab. This isn't a game where the story is anything important at all, but basically some scientists accidentally created these evil monsters whose color is just outside the visible spectrum. So they DNA modified this dude to be able to see them, and that's all, yeah, he just goes around killing them. Let's make the UI now. All text and icons display in a bluish color and are covered up with this red effect. It's not as well hidden as the enemies, and that's because of something I didn't know about 3D glasses until now. So the red lens only lets red light through, that's obvious, but the blue one, it's actually more like cyan. Because you can see both green and blue through it, it's impossible to hide it as well. The eye floater is in one channel and the other to cover it. But here I have to put the text in both the G and B channels, and that leaves only one for the cover up. So it's still kinda visible, but that's the best I could achieve. You can have 4 bullets max and each enemy takes 2 to defeat. I kinda want the gameplay of this game to revolve around managing your ammo and making sure you don't waste any. For example, in this room, the only way to proceed is to shoot this target block. If you played correctly, you should have exactly 1 bullet by now. If not, you must go back and retrieve anything you left behind. This game feels really cool with the glasses already. You'll just have to trust me on this one, since I can't properly show on video how it feels like when you're looking with both your eyes. I made this scene with an elevator that takes you to the basement. And after you go down there, it's like more infected or something, the details don't matter. When you go down there, there's fake walls and paths everywhere to confuse you when you're focusing on the red lens. There's a lot of red things in here, just like this big red subscribe button. Wait, it's not even red anymore. What is YouTube doing with their platform, man? I was also forced to make a restart button because in some rooms there are puzzles where you can get stuck if you don't shoot your bullets in the right order. Here you need to open this gate first and then take more ammo from the box to kill the enemy. And then you... wait, did you hear that? Yeah, me neither. The sound effects in this game are kinda non-existent. Now I usually just like to take no copyright free sounds online, but this time let's try recording my own. I mean, it can't be that hard, right? I would also love to make the music myself, however that's a topic for a whole other video. Anyway, let's continue with the game. I want the player to feel lost and confused while playing, so in this one room some parts change while they're off screen, forcing you to backtrack a bit and surprising you with enemies that come out of nowhere. The map is barely, or sometimes not at all, visible anyway, so you're not sure if you just saw it wrong or if it's the game that's tripping. Later on you can take another elevator to the exit floor. In this level I introduced blue hazards, so you have to either remember how they move and where they are, or actively look for danger with both eyes. It makes for some quite fun gameplay. By the way, after you finish watching this, you can check out this game on itch. It's not that good, most of the sprites are hand drawn in a few minutes because I just wanted to test out this anaglyph glasses idea. It would be a lot more trippy if the whole game was made in 3D, so comment if you wanna see me revisit this idea in another project. Also if you have more ideas on how to use this gimmick, because I'm not sure what else to do with it. This game was supposed to be longer, but I just don't know what to add. So if you clear all the rooms, you can exit the lab and win. Here's some more gameplay with the noise effect. I'm really sad that YouTube kills the quality, well at least I heard it does, I learned more for sure after uploading. Anyway, big thanks to all my channel members, there's not a lot of them. You should also join, the perks are like 1 emoji or something. So, thank you so much for watching, remember to subscribe, bye, meow!
Oh, Saturday, you are simply glorious.
That's right, Max. Glorioso.
You wake up.
What happens when a 4D creature moves around in a 4D world? What does it even look like? Normally when people refer to 4D, they refer to our 3D space plus time as the 4th dimension. But what I'm talking about here is another spatial dimension that we can move through or rotate in freely. That means new shapes, more degrees of freedom, and more craziness. So how does this work? In 3D, we have X, Y, and Z, which corresponds to left and right, up and down, and forwards and backwards. When we move to 4D, we add W, which corresponds to the directions Ana and Kata. Here I've just drawn an arbitrary direction because technically there is no correct way to draw this in a 3D view. So that begs the question, how do we truly see things in 4D? Trying to visualize 4D is a bit like trying to imagine a new color. Nobody knows how to do it. By the way, that's not a new color, that's just caramel. That being said, there are still ways we can understand the space. Imagine you are a 2D being that's just been thrust into a 3D world. Setting aside the imminent freakout and existential crisis, you would probably notice a few things. First, you notice that things seem to just appear and disappear from view, often contorting in weird ways. This is because your vision is now a cross-section of this 3D world, so things only appear to you if they're inside your cross-section. Before, you could only go horizontally or vertically, but now you can travel forwards or backwards, or even rotate in new ways. From our 2D perspective, this looks a little strange, but from 3D, we can see it actually makes perfect sense. Using this knowledge, we can see how a 3D view works inside a 4D world. Everything here might look 3D, but none of it actually is. These are all 4D shapes. Wait a minute, what are 4D shapes? Well, in some cases, 4D shapes generalize from 3D and 2D. Let's take a square. If we clone this square and connect the corners, we've now formed a cube. Now if we take this cube, clone it, and connect all those corners, we've now formed a tesseract, which is the 4D analog of a cube. And get this, if we spin this in a weird way, we are now able to start our new career as a Wikipedia article. We can also go beyond 4D simply by repeating this cloning and connecting process. Each time we do it, we go up another dimension, eventually ending up with a 10D shape known as the Decaract. Yes, that headache you're feeling is normal. Another way we can generalize 4D shapes is with circles. Simply put, a point on a circle is always exactly one radius away from its center. This concept generalizes beautifully to spheres, and, as you might have guessed, a hypersphere, which is the 4D analog of a sphere. We can take the square and circle concepts and combine them together. This gives us two new 4D shapes called the cubinder and the sphereinder. Then there are things that pretty much don't generalize, like duoprisms, which come from combining two separate 2D shapes together along different axes. As you can tell, this analysis is severely limited by my lack of understanding of what I'm doing. But when has that ever stopped me before? Let's move on to rotations. Now, in the past, I've explained rotations in 3D as sticking a skewer through an object and twisting it. And while this makes sense in 3D, it's not entirely accurate. Rotations are 2D operations. Literally any rotation, in any dimension, happens on a pair of axes. For example, let's take yaw. Normally I would represent this as rotating around the y-axis, but in reality, the rotation is only creating motion on the x and z axes. So it actually makes more sense to define the rotation as xz, or in general, the two axes that the rotation actually affects. This is especially important in 4D. By finding all the unique pairs of x, y, z, w, we can see that there are 6 different rotational planes. For anyone who's curious, I actually figured out how to calculate how many rotational planes any dimension has, which made me feel like a genius, until I found out some baguettes muncher had already done that 400 years ago. Another thing to realize is that when we rotate in 4D, there are now 2 axes that aren't being used, which is enough for another rotation. So 4D has this unique property where we can perform 2 unique rotations to the same object at the same time without them interfering with each other, which we call a double rotation. Alright, hopefully you're still with me because that's all the 4D we need to know. So that brings us to the next question. How the hell did I implement all this? Let me just clarify that this question alone could warrant 3 different videos, so I'm just going to summarize what happened. If you would like some more in-depth videos about this, let me know in the comments. Alright, our first problem is the transformation matrix. In a 3D game, we use this 4x4 matrix of numbers to position, rotate, and scale things, so logically, we would need a 5x5 matrix to achieve the same thing in 4D. Now, an important part of matrices is being able to invert them, which is a little expensive on a 4x4, but surely it can't be that much worse on a 5x5. Oh no. Luckily, you don't really need the extra row and column, because you can just work with the 4x4 and add an extra operation to include the position, which made this wonderfully easy to implement, and I was able to add this without much trouble. Next, we have to render the models. This is tricky. In 3D, meshes are made out of triangles, a 2D shape with 3 points, 3 edges, and 1 face. When we leap to 4D, we make meshes out of tetrahedra, which are the 3D analog of triangles, featuring 4 points, 6 edges, 4 faces, and 1 3D cell. For anyone who's curious, I actually managed to figure out how many features a piece of a mesh in any dimension would have, which... Wait a minute, I've seen this before. Wait, no.
Why are you everywhere? Why is this everywhere? How is it always linked to this goddamn triangle?
Today, business happens virtually everywhere. That's why you need Supermobile from T-Mobile.
Now, we've established that 4D meshes are sets of tetrahedra, but how did I draw them to the screen? Well, first, you gotta send in 4D meshes to the GPU, which I did by manipulating the vertex data you would normally send in 3D, so it was sending in tetrahedra data in 4D. So I was essentially Trojan horsing the GPU with 4D models.
It's 4D! Get it!
Next, you have to clip down the 4D models to the portion that is visible in our 3D view, meaning that each tetrahedron is rendered as up to 2 triangles. Normally, this would create a complex and lengthy shader, but you can just brute force all the possibilities offline and reference them in a lookup texture. It took a few attempts to get this right, but eventually I got it working. If this sounds familiar, it's because I learned how to do this by annoying Code Parade on Discord until he explained it like I was 5 years old. Shout out to Code Parade, awesome programmer, and he made a pretty cool game about this topic, so be sure to check that out. Finally, I need to actually create the 4D models. This is a little tricky. You do have this program called Mirrortope, which can generate some of the 4D primitives, but in general I made most of my models using custom scripts. This included extrusion, procedural terrain, and even creating a 4D pyramid, which was just generating 3D mazes for each level and making sure they were connected. Yeah, this was not fun. Let's talk about physics. This was even less fun. In order to implement 4D physics, I had to learn a whole new form of maths called geometric algebra, and by learning geometric algebra, I found that the equations in physics engines can be generalized to any dimension. Why? Well, some things in life are mysterious. Why does Pascal's triangle keep popping up? Why does my Discord think I'm American? Why does the preview of my 4D materials look like a condom? Nobody knows. No, the real reason is that geometric algebra shows us that some of the things you learn in 3D are actually specific instances of ideas that work in any dimension. Rotors are a great example of this. Rotors create rotations. In 3D, they are defined as a scalar and 3 bivectors, identical to a quaternion, a common component in most game engines. I swear, does anyone even listen to this? Alright, I'm just making sure. In 4D, rotors have a scalar, 6 bivectors, and a quad vector, which sounds weird, but it helps track the double rotations. So rotors can be expressed in any dimension, as long as you know how many groups with Welcome back, my petit fleur. So as I was working with geometric algebra, I realized that everything I was using followed patterns, so why not program them? This led me to creating a geometric algebra compiler in Python, which meant I could simply write whatever function I needed and it would give me the code to integrate it into my 4D engine. This also means I can compile expressions for any dimension, which is pretty cool. Maybe I'll attempt a 10-dimensional AI in the future. Now that I had this compiler, I could convert all the 3D physics maths into 4D with barely any effort. Obviously there's a lot I'm not touching on here, but again, we would need a whole video to discuss this. Alright, I feel like we've arrived at a great place, physically, mentally, geometrically, and we can now fully appreciate what comes next, the AI. Let's do this one more time. Since this is 4D, our AI will have a 4D body composed of a hypersphere, 8 tesseract legs, and 30 eyes, so it's basically a 4D spider. It's also 1.7 meters tall and takes up roughly 0.9 meters hypercubed of space, or if you're American, well, that didn't make much sense to begin with. So our 8-legged 4D friend will also be running a small neural network, trained with reinforcement learning. The AI will also be able to control itself by applying torque, meaning it's essentially a 4D wheel. It will be able to see things using depth sensors through its 30 eyes, and it'll be rewarded by how well it moves in the direction we command it to. So a simple setup for a sophisticated system. Let's see the training. After 11 hours of training, we can now see that the AI appears to have mastered 4D movement. But let's put this to the test. A couple of weeks ago, I accidentally tripped over and spilled all my orange M&M's all over this 4D world while double spraining my ankle. Now it's up to the AI to get all this food back. Good luck, 4D Spider.
Grip, stability, precision. That's the essence of driving. Lawfin.
the rarest move in chess. I know what you're thinking. You think you have all the answers. I was like you once. It's gotta be en passant checkmate, right? You know, the weird pawn move done in a way to cause checkmate. Or, wait, maybe castling checkmate is more rare. Or something with pawn under promotion. There's a simple way to get to the bottom of this. Let's just look at a bunch of games of chess. Whatever happens the least often must be the rarest, right? Like, if we ask a million people what their favorite type of pizza is, we could find the most rare pizza topping, which we already know is rhubarb. If we want to do this, we needed some way of talking about moves. Like, what is a rare move? What even is a move? What does it mean to play chess? What are we doing again? Okay, we're going to talk about moves in terms of standard algebraic notation. That's the normal way people talk about chess moves. Like when they say e4 and nf6. It's what they're writing down on those little pieces of paper. It's a simple notation. You just say what piece moved where. That's the basic idea, at least. We just need to give names to places and pieces. So we give every square on the board coordinates with a letter and number, and we give every piece a letter of its own. We can use these letters and numbers to write down moves, like bc4 means the bishop moves to c4. And there's only a couple extra things to know. X means capture, nx f3 means the knight captures the piece on f3. Pawn moves don't bother with naming the piece. e5 just means you move your pawn to e5. You add a plus to indicate a check. qa5 plus means your queen moves to a5 and the opponent's king is now in check. And similarly, the hash sign means checkmate. Pound sign? What do you call this thing? Octothorpe. Yeah, means checkmate. Kingside castle